Hi, hello. In the previous class, we saw there are certain drawbacks or defects for the Bohr model of hydrogen atom. And of course, as the name implies, it is applicable only for hydrogen atom. The Bohr model is applicable only for hydrogen atom. So, what are the drawbacks? One, it is only applicable to one electron system. It could not explain the spectrum of polyatomic, polyelectronic or polyatomic atoms, or polyelectronic, you can say more than one electron system. It cannot explain its spectrum because spectrum is the fingerprint of an atom. That model is having certain drawbacks. Similarly, it shows some contradiction with Heisenberg's uncertainty principle, which we have not yet discussed. So all these were the certain difficulties of what is so called the Bohr model of hydrogen atom. Remember one thing, on those days, the scientific world follows what is so called classical mechanics. You may ask, what is classical mechanics? Nothing other than the principle based on Newton's theory. You know the first law, second law, third law of Newton's laws of motions. So based on that, there was a mechanics that is known as classical mechanics, and with the help of classical mechanics, the scientific world could be able to explain the motion of macroscopic particles. And so even they could be able to explain how the planets are revolving the sun and the revolution of moon around the earth, like that. They could be able to explain based on what is called the classical mechanics. So anyhow, there is a scenario that we are going to what is called we are going to deal with what is called the microscopic moving particle like electron. So whenever we are dealing with the microscopic moving particle like electron, there face certain difficulties. So we'll come to those what are the difficulties later. So let us start with the discussion of, so we are going to some problems facing on those era. So uh, in order to discuss those problems, we will not discuss that problem to be discussed. We'll come to that point later. So in order to get a much more better idea about the difficulty of the problem, okay, difficulty level of the problem, we will discuss certain other points. The first one is Louis de Broglie hypothesis, or we may call it as Louis de Broglie equation. What is that? It is a concept of wave-particle duality of matter. What's the learns of that? See, on those days, actually these are the beginning of the 19th century, on those days actually Einstein proposed that the radiation or light possesses dual nature. What do you mean by the dual nature of radiation? It have both the characteristic property that it possesses a wave-like nature as well as a particle nature. Both are possessed by the radiation, which was proposed by Einstein. So whenever the light propagates in a medium, it will possess wave nature, while whenever it interacts with the matter, it's like photoelectric effect, it shows particle nature. So that was the idea proposed by Einstein. So the similar idea was proposed by Louis de Broglie also, and he proposed a wave-particle duality of matter, which means all the form of matter. It could be a cricket ball, it could be a football, it could be a car, whatever it may be. Whenever you are discussing about their motion, it possesses some wave-like nature also. That is the idea proposed by Louis de Broglie. And you may wonder by saying like that, a car which is moving has a wave-like nature like that. So we'll come to that point as the discussion progresses. You will get much more better idea. So we'll discuss about the de Broglie hypothesis. He was a French physicist, and he proposed the idea that if waves can have a particle-like characteristics, then can particles such as electron have wavelength characteristics? Let us check. And he proposed an equation which is very familiar called the Broglie's equation. And this was the equation lambda. Lambda is equal to h by mv, where lambda is called the wavelength of matter waves. What do you mean matter waves? The wave created by a matter is known as matter wave. Its wavelength is measured as lambda here. H is Planck's constant, very well, and m is the mass of the substance which you are interested with. V is the velocity. And they are given the unit also. Wavelength must be in meter. We are discussing in SI unit. Velocity must be in meter per second, and mass must be in kilogram, and H is Planck's constant in joule per fluids. That is 6.6 into 10 raised to minus 34. That is the value of what is called the Planck's constant value. Then, what this equation do? Tell us that all moving particles have wavelength characteristics. Let us check. And I told you a car, a baseball, and whatever it may be. Do these have wavelength characteristics? Why or why not? Okay, we'll check. Lambda is equal to h by mv. The car and the baseball do have a velocity and a mass, of course. Using the Broglie equation, let us calculate the wavelength of the movement of a baseball or a car. Okay, say mass of the car approximately taken a mass as 9-10 kg, and it is, let us say, it is moving with a velocity of 25 meters per second. And so, if you calculate the wavelength by applying the above expression lambda equal to h by mv, the value will be 2.9 into 10 raised to minus 38 meter. See, check the 2.9 into 10 raised to minus 38 meter, meaning that value is very small, isn't it? So, what is wavelength? Wavelength is the distance between two consecutive crusts or trough. So, if you draw a wave, then what happens? The distance between the two crusts becomes very small. That means the wave will merge together. If the waves are merged, then what happens? Definitely we cannot detect the wavelength. With whatever microscope you have, whatever the sophisticated equipment you have, this much small wavelength you cannot measure. Okay. Now, if you take this piece of electron, it is moving with a speed of 25 meters per second, and the mass of electron, 9.1 into 10 raised to minus 38 gram, which if you apply, you will get a wavelength as 2.9 into 10 raised to minus 5 meter. And of course, this is a measurable wavelength. If you have a good equipment, definitely you can measure it. Clear? So, what you can say is, actually, here we are seeing two kinds of particles. One is a macroscopic particle, the other one is microscopic particle. So, all the kind of particle or all the form of matter possess the wave-like nature. Of course, they possess a particle nature. Anything having mass and velocity, you can say it possesses a momentum or a particle-like nature. So, all the matter have, if it is in a moving situation, definitely possess a wave-like nature also. But for macroscopic particles, since the wavelength is too small, we cannot measure it. But in the case of an electron, it is a measurable quantity. Not only electron, all the microscopic particles possess a considerable wavelength which is measurable. Yeah? So we can conclude as microscopic moving particle like electron possess a wave particle duality. That is a conclusion. That is a proposal made by Broglie Eqn. So, in that era, this is one of the revolutionary proposal made by the scientist called Broglie. and we have some more developments in science on those days, and we will discuss that one also, and we will continue in the next session.